Okay, how many of you have the textbook, the access code? You're the only one? There's one eager beaver in here. So did you get it over the textbook over to the store here? Okay, so when you log into Blackboard, so then there will be a list of courses that you can log on to, and your list of courses will be, of course, different from mine. But Computer Science 1300, okay, in the spring of 2012 should be one of them. And so when you log on, you'll get the student view here. Okay. So do you get something like that? So now these are the things that are immediately available, okay? The slides, okay, for the course. And today I'm going to be talking about CO1, okay? And so the agenda, the syllabus, the TA. This was the stuff I did on buying a computer. This is the ISBN. So is this your, is this the ISBN that you got? That's your ISBN? Do you have it with you?
I have the access code. I don't have the...
Okay. Okay. The reason I bring that up is there are, Cengage actually has two products that are very similar. And sometimes they get mixed up about that. Okay, so anyway, you'll have over here SCORM, S-C-O-R-M, and so you click on SCORM, and that should come up with a merge with computers. Okay, here. What does yours say? Does it say exactly the same thing? This you merge with computers V2F. Does it say F11? Well, no, let me not have it set up yet, okay? But that would be fall of 11, okay? So I hope they've got it set up, or you click on that. Okay, well, do you get the same thing I get here? Okay, so it does not contain any. All right, so the people in Blackboard haven't set it up yet, okay? Same thing?
Yeah.
Exactly the same thing? Well, what does it show?
It shows like system requirements and
Sorry? Yeah, we don't have it yet. Okay. So, only one of you is the only got the access code? You, okay, so are you able to get on? What? You're working on it, okay. All right, anyway, we'll be looking at that maybe next time. Okay, so today I want to talk about digital technology, and also I want to talk about, I guess, just operating systems and internet, okay? So your first assignment is going to be to write a research paper using Microsoft Word, you know, or Mac Word, and it's going to be a 4-page paper. And so you have to use, you know, the operating system, and you have to use the internet, okay? So I think you won't have any problem with this. I think everybody knows enough about the operating system, okay? But let's talk about it just a little bit, just to make sure. What is Internet Explorer? What is that? It's a browser. What's a browser?
Search engine.
So it's a piece of software that basically you use to browse the internet, right? And this Internet Explorer is made by Microsoft, right? So there's some other browsers besides Internet Explorer. What are some other browsers? Firefox. Okay, and another one. Safari. Okay, another one. What? I can't hear you. Netscape. Okay, there's a lot of browsers, okay? And but the two most popular ones, I would say, are Internet Explorer and Firefox, okay? So that's Internet Explorer, okay? Now, what is Windows Explorer? What's that? What's the difference in Internet Explorer and Windows Explorer? They're both produced by Microsoft. You know, Internet Explorer explores the internet, and Windows Explorer only explores your own computer. Not the whole internet, just the stuff that's on your own computer and nobody else's. Okay. What's on your own computer? Well, you know, your computer is set up as the data on your computer is in a bunch of folders, right? So basically, on your computer, when you talk about the file structure, the file structure is in folders, okay? And these folders, you know, we think of as being just like a manila folder, right? And each one of these manila folders has a name, right? And so there's a whole bunch of these folders, right? And what's everything is sort of in one big folder. I mean, these folders can have other folders inside of them, right? Or these folders can have files. So sort of, what's the big folder? The big folder that sort of contains all the other folders. There's one big folder. Yeah, it was used to be called C:, right? And basically that's all the stuff that's on your C disk, right? There's another folder called D:, right? Usually. There may be a folder called A:, or B:, or C:, depending on your computer, right? The most important one is C:, which is now called OS as well. So, do you know how to navigate around and all this stuff? Can you create a new folder? Do you know how to create a new folder? And do you know how to put a file in a new folder? Okay, well, I'll tell you what, let's do. Let's just give it a try, all right? Let's start here. This little icon right here is this is Windows Explorer down here, see? This is Internet Explorer, the E, and this is Windows Explorer down here. So let's just double click on Windows Explorer, okay? And so here we are in a folder called Libraries. And Libraries has some subfolders: Documents, Music, Pictures, and Videos. Okay? So let's double click on Documents, okay? And in the Documents folder is, you know, other folders. Okay, here is yet another folder, two other folders, and then these are some actual files. Okay. All right, let's go to this Documents folder and let's create two more files. Let's create a file called Republicans and another file called Democrats. Okay. So in the Documents folder, create two subfolders. And then let's bring up Internet Explorer and get a picture of President Obama and put President Obama's picture in the Democrats folder. Okay. And then get a picture of Newt Gingrich. Put him in the Republican folder. Here. You know how to do that? Everybody do that? Yeah. if you don't have a my document, let's make it in desktop again. See that these computers are all set up exactly the same. Anyway, anybody done this? Okay, so I've been having some students. So basically, I would have to say in some folder. Okay, since all these computers are not set up the same, I would have thought they all would have my documents folder, but some of them don't. So anyway, this is just basic stuff that you have to know how to do. So. We kind of assume everybody knows how to do that, right? And so if you have trouble doing this, you need to see me after class, and we need to set you up with a little private, session with the TA, But if this is something that seems fairly reasonable, then no problem. Okay, how many have been able to do this so far? You got the two pictures? Okay, good. Okay, so we'll just stop there. Okay, I want to talk about digital technology, okay? So this is the first actual lecture in the course, and this is found in the slides, section on your Blackboard page, and it's also chapter CO1 or in the textbook. Okay, so digital technology. Okay, digital technology. What is digital technology? Allows us to manipulate all types of information as digits, ones and zeros, in order to store and manage the information more efficiently and effectively. So we talk about two types of technology mainly. Digital technology. And analog technology. That's an A. So what's the difference between digital technology and analog technology? Well, analog technology was sort of the older technology, sort of the pre-digital technology. If you go back, say, to the 1930s, 1940s, most of the technology around at that time was analog technology. And what does that mean, analog technology versus digital technology? Yeah. What is a continuum? What's your view of the universe that we live in?
It's endless.
Can you think of a one-dimensional continuum? In mathematics, that's, I guess, one of the main concepts, okay? A line, okay? And so mathematicians have a line, okay? And they'll put a 0 somewhere and a 1 somewhere. And that'll mark off a distance, and then they'll use that same distance to mark off a 2 and a 3. Okay? And then over here they'll mark off a -1. And that line is a one-dimensional continuum. And what does continuum mean? Well, it means that we think of that line. See, this is a Platonic, notion. Okay, a Platonic ideal. A line, it's straight, has no see, it's not like the one I actually drew. This line is absolutely straight, okay? One-dimensional, okay? And every point on that line represents a distance from 0. Okay? You can pick any point in here. So let's suppose you picked out the distance pi. .14, 159,265, blah blah blah. Okay. Every point, it doesn't matter which point that it's an actual point on the line. And we think of all those points as being there. Okay. So what's a two-dimensional continuum? This has an x and a y, right? And what's a three-dimensional continuum? Well, three-dimensional continuum, has a x and a y and a z. Now, we can imagine that we live in a three-dimensional continuum. That is, every place you can actually be has an x, y, z coordinate. And we can pick an origin anywhere you want, okay? And you can move around the universe anywhere. And you're at some x, y, z coordinate, okay, in this continuum. And sometimes we let time be the fourth dimension, okay? And so we say, at time t, you are at place x, y, z, right? And basically, if you just sort of plotted where you are at every point in time, okay, you are basically traveling in a four-dimensional, line, curve in this time-space continuum. Right? Now, the thing about this continuum, let's go back to a one-dimensional continuum. See, I can make 0 right here, and I can make 1 at the other edge of the room again. Now, I can walk anywhere in between these two, right? I can be at 1/10. Okay. I can back and forth. Any place I am, any point on that line, I can walk back and forth. It's a continuum. Yeah. Now, analog. I mean, this is kind of a basis for the way we think of the universe, right? And analog technology is sort of based on this notion of a continuum. Okay. So, for instance, how do they make clocks or watches? Well, these little hands, you know, go around, you know, smoothly, right? And this watch is an analog, you know, device based on this continuum. On the other hand, a digital view of the world is different. A digital view is you can't just go any place between here and there. There's some little small unit that you can't go less than that. I go one of these teensy little units, two of these. So digital is a discrete, like that. Okay? And so any instrument, okay, that works on that basis is a digital instrument. So the difference between analog and digital is the difference between a continuum notion of the universe and a discrete, you know, time. Okay, so in this section we talk about digital literacy and computing platforms. Digital literacy, an understanding of how computers represent different types of data with digits, and how the usefulness of that representation assists people. Computer literacy, bits and bytes, digitization, ASCII, binary, digital convergence. Well, what sort of things can be stored on a computer? We can store numbers. These numbers will be stored on the computer. We can compute with these numbers. Okay. The computer can add them, subtract them, multiply them, divide them. You know, just like you and I can. Okay. You can do some very serious, you know, computations. So we can store numbers on our computer. We can also store text. We can store the letter A, the capital letter A, the small letter A. Okay. We can also store these numbers as text. That is, the number 1, you can either store as a number and compute with it, or you can store it as just a piece of text, okay, just like the letter A. There's actually 2 different ways of storing the number 1. The text way and the number way. You take the number 83, you can store that as a number, or you can store that as 2 text characters. What else can you store besides numbers and text? Well, we can store pictures. We can store sound. We can store movies. And there's some other things we can store. But how do we store these things on a computer? In fact, we don't store them the same way. We don't store numbers the same way we store text. And we don't store text the same way we store pictures, okay? And we don't store any of that the same way we store sound or movies, okay? We store all these things different ways. But in the final analysis, if we look at it, all of these different ways of storing these things are just a series of zeros and ones. Okay? All right. How do we store numbers? Okay. Well, the most usual way of storing numbers on a computer is called the binary number system. And the way you store a 0 is 1 bit, 0. And the way you store a 1 is 1. And the way you store 2 is 1 0. And the way you store 3 is 1 1. And the way you store 4 is 1 0 0. 5 1 1. 6 7 8. Okay. Now, so the bigger the number, the more zeros and ones it takes to store it. And the underlying idea here is powers of 2. It's a place position. It's a position oriented. Now, in your head, you store numbers like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's also true the way you store numbers in your head. The bigger the number, the more digits it takes to store it, right? And it's a positional notation. And we talk about the ones position, the tens position, the 100s position, the 1000s position, okay, the 10,000s position, and so forth. Okay. So the numbers 0, 1, 2, up to 9 can all be stored in the ones position. But the number 10 has to be stored like this. And the numbers from 10 to 99 take 2 positions. Okay? But 100 takes 3 positions. Okay? And so forth. Another way of saying that is we have the ones. The ones position is the 10 to the 0th power. You know anything to the 0th power is equal to 1, right? You know that? Everybody know that? Anything raised to the 0th power is equal to 1. So there's the 10 to the 0th power position. There's the 10 to the 1's position. The 10 to the 2's position, see that's 100. The 10 to the 3's position, that's 1,000. the 10 to the 4's position, you know, it's 10,000. And so 1 through, 0 through 9, 10, 100. That's the tens number system, okay? That's what we've been taught since childhood. And why do we use 10? Because you can use basically any number system you want. We say the basis of our number system is 10, okay? That means the positions are powers of 10. They say because we have 10 fingers and 10 toes. So the binary number system is just the same idea, except the positions are powers of 2. So you have the 1's position, the 2's position, the 4's position, the 8's position, the 16's position, the 32 position, 64 position. So this is the 2 to the 0th position, 2 to the 1 position, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So we have 0, 1, 2, 3, okay? 4, 5, 6, 7, Why do computers store numbers in this strange binary system? Why don't you just use the tens number system like we do? Well, in fact, they could. You can build a computer that uses the tens number system, just like we do. There have been computers built, in fact, that do that. The little calculators that you use in your hand and do calculations, those use the basis 10, power 10, and just like we do. So you can do that. The reason that computers use this binary number system is it's faster and easier and doesn't cost as much money. It's very easy to put in zeros and ones, okay? And so it's basically a matter of speed and money. Anyway, you never see these strange binary numbers anyway. Okay? When you enter your numbers into the computer, you enter them in as base 10 numbers like you're used to. The computer converts them into these binary things you never see, right? And it does all of its stuff in binary, and then when it gets its answer, it converts it back to base 10 before you see it. Okay? I mean, you don't need to know about that unless you're a computer scientist. You need to know, okay? Because sometimes you have to look at when things go wrong. You have to look at core dumps and things like that. So you got to know what's going on, But most people don't need to know that, right? But I think it's an interesting thing. Right? So that's how they store numbers. And another thing, it's very easy to build circuitry that will add these numbers, okay, these binary numbers, okay? It's much easier to add in binary than it is in decimal. In decimal, suppose we wanted to add 25 and 37. How do you add 25 and 37? And he's like, well, 5 plus 7 is 12, okay? How'd you know that? You gotta memorize. You gotta memorize these, one-digit things you gotta memorize. You gotta remember 5 plus 7 is 12, okay? That's a 2 and a carry of 1, right? And then you add the 1 plus the 2 plus the 3, you get a 6, okay? That's how we add, that's how you add, right? ever since childhood. How would you add those in binary? Well, first of all, you got to express 25 in binary. And how do you express 25 in binary? Well, so you've got 1, 2, 4, 8, 16. 25 would be 16 plus 8 plus 1. Okay. That's 25. In binary, 25 looks like this. 1, 1, 0, 0, 1. How does 37 look in binary? Well, you got 1, 2, 4, 8, 16, 32. That's 32. I need 5 more. That's 4 plus 1. Okay. So 32 looks like this. 1, 0, 0, 1, 0, 1. Oops. Yeah. So this is 25, 1, 1, 0, 0, 1, and 37 is 1, 0, 0, 1, 0, 1. So let's add them. 1 plus 1 is 2. That's 0, and a carry 1. 1 plus 0 is 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 1. Is that 62? Well, this is the 1's position. This is the 2's position. 4's position. 8's position. 16's position, 32. It's 32 plus 16 plus 8 plus 4 plus 2, but not a 1. That's 62. So it's really easier, you know, to do arithmetic in binary, which is another reason why these computers use binary. Well, what about fractions? How about 0.5? How do you do that in binary? How about 0.6291? 0.6291. How do you do that in binary? But no problem. You do it the same way in decimal as you do in decimal. In binary, you don't have a decimal point, you have a binary point. And over here, on this side of the binary point, you have this is the 1's position, the 2's position, the 4's position, the 8's position. Okay. On the other side, you know, of the binary point, you have the 1/2's position, the 1/4's position, the 1/8's position, the 1/16's position. I mean, in decimal, you see, you've got 1, 10, 100. Over here, you have 1/10. Here you have 1/100, 1/1000. So basically, you can have you know, fractions and all that kind of stuff. Okay, and so you can do arithmetic very well in binary. So that's how you store numbers, at least those numbers that you compute with. Okay, on a computer, you store in the binary number system. How do you store letters and text? I mean, when you enter data on the keyboard, how do you enter the letter capital A? How do you enter a little a? How do you enter a 3? Not as a number to compute with, but just as text. Okay. How do you enter a question mark? or an equal sign, or an open parenthesis there. Open parenthesis. Well, you don't use the binary number system, okay? But you still use zeros and ones, okay? And basically, you just have to have a code for that. You just got to come up with a set of zeros and ones that mean capital A, another set of zeros and ones that mean a little a, another set of zeros and ones that means a text 3, question mark, again. Well, how many zeros and ones does it take to do a capital A, little a, 3? Just depends on your code. So we have for many, many years in the computer business used something called the ASCII code. That stands for the American Standard Code for Information Interchange. ASCII. You know, we have a American Standards Institute, right? It's in I guess Washington, okay, D.C., a suburb of Washington somewhere, and they came up with this code, okay. It's an 8-bit code, okay. That is, every character is stored as 8 binary bits. That is a set of 8 zeros and ones. ASCII, A-S-C-I-I. Let's go to the internet. And let's Google it again. Just Google. ASCII. A-S-C-I. Okay. ASCII to Wikipedia. ASCII table. I mean ASCII, not ASCII 2. Come on, come on. Didn't give it to us. Well, no, there again. Finally got her again. So here is the ASCII table. So let's look for a capital A in here somewhere. Here's a capital A right here. Oops. Can you see that capital A there? 65, 41, 101, ampersand star 65. Oh gosh. What is all that stuff? my little problems here. A. It says 65. 41, 101, ampersand, pound sign, 65. That's how you do a capital A in ASCII. This is the decimal representation of it, okay? This is the hexadecimal representation of it. This is the octal representation of it. And this is the HTML. Good. So A, capital A, decimal 65, hexadecimal 41, octal 101, HTML, ampersand, pound. Wonderful. I wanted to know how to do it in binary. It's 8 binary bits, okay? Now, octal is to the base 8. Hexadecimal is to the base 16. Decimal is to the base 10. I can change this octal into binary, okay, because this octal number here, this is the 1's position, the 8's position, and the 64's position, okay? That's 1, 8, 8 squared. 101, okay? 64 plus 1 is 65, right? Well, in binary, I have got 1, 2, 4, 8, 16, 32, 64. In binary, it's just a 64 and an 8 and a 1. Okay? So it's 1, 0, 0, 1. So the binary code for a capital A is 1 and then 6 zeros. I mean, sorry, 5 zeros. Another 1. Yeah. A capital B is this. Okay. Capital C is this. So it's basically a code. And you know, in computers, you know what a bit is, a bit and a byte, right? What's a bit? A bit is a one binary character, a 0 or a 1. Okay? A byte is 8 bits. Okay. And in fact, computers are all organized. The memory of a computer is all organized in bytes. Okay. We've got the memory of a computer has got byte 0, byte 1, byte 2, byte 3, byte 4, byte 5. However many bytes you have. Okay. In each byte, you can store 1 character. So here's the ASCII code here. Notice it has it actually starts a space is octal 40, okay, which would be in binary, okay, this would be 3 zeros, the 4 would be a 1 and 2 zeros. And decimal, it's a 32nd character, so starting at decimal 0, 1, 2, 3, 4, 5, the 32nd character in the ASCII code is a space. Notice that space is a character. Now, when we write things, okay, or look at things, we don't give much credence to spaces, do we? I mean, a space is not something we sort of concentrate on, right? And we don't really care between words if there's 1 space or 2 spaces or 3 spaces, although we like for it to be kind of consistent, right? However, in computers, you know, a space is just as important as an A or a B or a C. Okay? And a space is not a 0. Okay? A 0 is something different from a space. Okay? There's also a null, N-U-L-L. Where's the null? Very first thing here, or I guess N-U-L. That's different from a space. I mean, if you had a computer and this was a byte here, and a byte here, and a byte here, okay? If you had the character A stored here, and a space stored here, and a B stored here, when you print it out, it would look like this: A, B, with the space in the middle. If you had A, and then here you had the null character, and a B, if you printed that out, it's going to be AB with nothing in the middle. Okay. So it has some little peculiarities to it, you know. The first characters over here in this ASCII are all special characters, okay, control characters, okay. And these things are used for different protocols. There's an ACK, that means acknowledge, and there's a NAC, which means don't acknowledge. There's a device control 1, device control 2, there's a line feed character, okay. There's a bill, there's a backspace, there's a horizontal tab, okay, a line feed, okay. All this other stuff for controlling the text, okay. So if you got some text in your computer, okay, and you print it out, when you get to a horizontal tab, it'll cause a tab, okay. Get a line feed, it'll go down to the next line, and all that. So now this A is actually in 8 bits, it's a 0, then a 1, and 5 zeros, and a 1. That's how this A is stored, okay, in a byte. That's an A, capital A. That's also the way you store the number 65. And if you store the number 65 in binary, you can compute with it. You store an A here. How do you know whether that's a capital A? It's a piece of, how do you know whether that's text, a capital A that's being stored there, or the number 65? It could be either one. How do you know? You don't. How does the computer know? It doesn't. And it doesn't care. Why should it care? if you add it to something, you just added 65, right? If you printed it out, you just printed a big A. Okay. Well, how do you store pictures? How do you store pictures on a computer? You do not use the binary number system, okay? You're not computing with pictures, okay? You do not use the ASCII code, okay? That's not a bunch of text, okay? So there's yet a different way you store pictures, okay? There's zillions of ways of storing pictures on a computer. The most common way is called JPEG. And if you have a picture and it's stored on a computer in JPEG, usually the name of the file will be something like my picture, whatever that picture is, .jpg. You know, this files are all stored. You have a file name dot a file type. The file name you just make up yourself, okay? The file type is how you're storing it, okay? And this file type tells you whether or not, it's going to be a binary number, or a text, okay, or a picture. Okay? What does JPEG stand for? I'm running out of time, aren't I? The Joint Photographic Experts Committee, or group. The Joint Photographic Experts Group. They were modest people. But years and years ago, all of the companies that were interested in storing storing pictures on a computer, got these people together, and they call themselves the Joint Photographic Experts Group. And they came up with this way of storing pictures. Okay? I have a book on this. It's really not that complicated, but they made a book like that. Okay, I'll continue there next time. I'm still on this C01. And so if you get the textbook, you can read chapter C01, okay? Con 01. You can look at the PowerPoint slides, okay? C01, okay? I'll be continuing there next time. Yes?
What is the
I believe on the agenda I showed that to be handed out in the third week. This I believe it says on the agenda that it's due the week after.
I'm the one who emailed you earlier about how I couldn't connect to VNet, and you told me that I wasn't in your list.
No, that's right, you're not. Let me just turn off this recording real fast.
Okay.
You don't want to